Hi everyone. Today I am going to discuss about second normal form. In last videos or last lecture, what is meant by normalization, what is the functional dependency, what is by first normal form. Okay, second normal form states that for every non-key attribute, for every non-key attribute, non-key attribute is fully functionally dependent on primary key, is fully functional on primary key. A relation schema R is in second normal form. For every non-key attribute is fully functional dependent on primary key. That is a second normal form. Second normal form input. What is input here? Input is 1NF. Output is a 2NF. Input is 1NF and then output is a 2NF. Second normal form, what is the main drawback of second normal form is the partial dependency. Okay, what is meant by partial dependency? For example, R of A, B, C is a relation. R of A, B, C. AB tends to C. A tends to C. B tends to C. The given functional dependency. R of A, B, C, R is a relation. A attribute, B attribute, and then C attribute. AB tends to C, A tends to C, B tends to C. Is a functional dependency. Observe here, for every non-key attribute is fully functionally dependent on, that is a primary key. What is the first? We find out candidate keys. That is a AB closure. What is AB closure? AB. AB derives what? That is a C. We can get the original relation. That's why AB is a candidate key. And whereas in the A closure, what is the A closure? A closure is a A and then C. A is not a key. And then B closure, B and then C. B is not a candidate key. That's why AB is a candidate key. Okay. And whereas in the A tends to C, B tends to C is a partial dependency. Is a part of candidate key. That's why this is a partial dependency. There is no partial dependency in second normal form. What is meant by partial dependency? Observe here, AB tends to C. For every non-key attribute is fully functional dependent on primary key, but whereas in the A tends to C, B tends to C is a partial or part of a primary key. That's why it is a partial dependency. That's why it is not in the second normal form. The given relation is not in the second normal form. That's why you can decompose into two smaller relations. Okay, that is the partial dependency. Observe here, second example, student table. Student table having student ID, course ID, course fee. And what is the student ID? 101, 102, 101, 103, 103, 102. Whereas in the course ID also there is Java, Python, C++, C, Java, JavaScripts, like course fee also. Observe here, that is a functional dependencies based on, that is a, probability of functional dependency. SID tends to CID. Observe here, SID tends to CID. SID tends to course fee. SID tends to, CID tends to course fee. SID, CID tends to course fee. SID course fee tends to CID. Course fee, CID tends to SID. These are the all combinations of functional dependency. Observe here, first one, SID tends to CID. And what is a 101 Java? Here that is a 101 Java, 101 C++. Observe here, first one, 101 Java, 101, C++. Okay, SID tends to CID. Functionally dependency is not satisfied. Why? Because based on the property, and what is the property here? T1 of x equal to T2 of x, T1 of y equal to T2 of y. Okay, observe here, tuple 101, 101 are same, but whereas on the right hand side are the difference. That's why functional dependency first one is not satisfied. Second one, functional dependency is not satisfied. Second one, SID tends to course fee. 101, 10,000. Here that is a, 101 to 1000, no problem. I mean next one 103, 103, that is a 10,000, again 103, 10,000, no issue. And what about here, that is a, I mean what is that, SID tends to course fee, SID tends to course fee, SID tends to course fee. And what is the here, SID tends to course fee 101, 10,000, here is there 101, 10,000, no. That is the next 102, 15,000, is there 102, 15,000, no. That is a 101, 2,000, right, 103, 10,000, and then 103, 10,000. Okay, that's why I mean SID tends to course fee. Next, CID tends to course fee. Observe here, CID tends to course fee. Java 10,000, Python 15,000, I mean C++ 2,000, I mean C 10,000, Java 10,000, JavaScript 2,000. Observe here, Java 10,000. Is there any Java 10,000? Okay, no problem. Python 15,000, right? Is there any Python 15,000? That's why CID tends to course, ID tends to course fee, functionally dependency is satisfied. And whereas in the SID CID tends to combination, SID CID tends to course fee, SID CID tends to 101 Java 10,000. Is there a 101 Java? No. 102 Python, 102 Python 15,000. Is there 102 Python? No. That's why SID CID tends to course fee, functionally dependency is satisfied. Okay, and then SID course fee tends to CID, SID course fee, that is a 101,000, I mean 10,000 Java. I mean here, I mean is there any 101 10,000? No. And then 103 10,000, and then 103 10,000, this tends to, I mean C and then Java. And left hand side, combination of left hand side same, whereas the right hand side not same. That's why functional dependency is not satisfied. I mean same like this also, functional dependency is not satisfied. Okay, observe here, that is a CID tends to, I mean course fee. What is the first one? SID tends to, I mean course fee, I mean SID, what is sorry, SID CID tends to course fee. SID CID tends to course fee, and then CID tends to course fee. Here for every non-key attribute is fully functional dependent on primary key, that is SID and CID. But whereas in the here CID tends to course fee is part of the primary key. That's why this table is not in the second normal form. That's why we can decompose into two smaller relations. What are the two smaller relations? I mean first one is the SID. I mean second one is the CID. It can decompose into two smaller relations. And what is the first one? 101 Java. I mean next 102 Python. I mean next 101 C++. I mean 103 C. 103 Java. I mean 102 JavaScript. Observe here SID CID is a primary key. Okay, observe here 101 Java. Is there any 101 Java? No. 102 Python. Is there any 102 Python? No. 101 C++. Is there any 101 C++? No. 103 C. Is there any 103 C? No. 103 Java. Is there any 103 Java? No duplication. 102 JavaScript. Is there any 102 JavaScript? No. That's why the relation is in second normal form. What is in by second normal form? For every non-key attribute is fully functionally dependent on primary key. That is the first relation. Whereas in the second relation is a CID tends to course fee. That is a relation, that is a R1. You can decompose into two relations. First R1, I mean second one R2. What is a CID tends to course fee? What is a CID? Java 10,000. Java 10,000, there are two times. Simply we can write as Java, I mean 10,000. I mean next one Python 15,000. Python 15,000. And then next one C++ 2000. C++ 2000. And then next C 10,000. There is a C 10,000. C 10,000. Observe here. After decomposition, relation R1 and R2 are second normal form. Why? Because here what is that? Here CID. After decomposition, CID is a primary key. Observe here, this is the second normal form. Before going to the, before decomposition, what is the student table? Student table is not in the second normal form. Why? Partial dependency is there. This is the first dependency, functional dependency is satisfied. Second one is the CID tends to course fee satisfied. Based on the functional dependency combination, what is the SID tends to CID, SID tends to course fee, CID tends to course fee, SID tends to course fee also, functional dependency is not satisfied. Here CID tends to course fee, CID tends to course fee. Why? Because observe here, CID tends to course fee, CID tends to course fee based on the functional dependency property. What is the Java 10,000? Java 10,000. What is the property? T1 of x equal to T2 of x, T1 of y equal to T2 of y. Left hand side are equal, whereas in the right hand side also same. That's why functional dependency is satisfied. Based on functional dependency, that is the these two are satisfied. That's why simply we can write as SID comma CID tends to course fee, CID tends to course fee. Clear? For every non-key attribute, that is a course fee is a non-key attribute. What are the key attributes? SID, CID is a carried key, but key attributes are SID comma CID. And what is the here? SID, CID tends to course fee for every non-key attribute is fully functionally dependent on primary key. First one okay. Whereas the second one, CID tends to course fee is a part of primary key. That's why the given table is not in the second normal form. We can decompose to small relation R1 and R2. After decomposition, the given two tables are in second normal form. That is the 2NF. Whereas in the GATE 2005, a table has fields F1, F2, F3, F4 and F5 with the following functional dependencies. And what is the F1 tends to F3, F2 tends to F4. F1 comma F2 tends to F5. In terms of normalization, this table is in first normal form, second normal form, third normal form and then none. Okay. Observe here, based on the functional dependency, what is the we find closure first? F1 closure. F1 closure. What is F1 closure? F1, F3. F1 closure, F1, F3. And then here F1 is not a candidate key. Why? Because we cannot get the original attributes F1, F2, F3, F4 and F5. Whereas in the F2 closure, we find F2 closure. F2 closure. What is F2 closure? F2, F4. We can't get original. Only we get F2 and F4. And remaining we miss the values F1, F3, F5. That's why F2 is not a candidate key. And then next F1, F2 closure. F1, F2 closure. F1, F2 closure based on the reflexive property F1, F2. What is F1? F1 tends to F3, that is the F1 derives F3, F2 derives F4, F1, F2 derives F5. We can get the original attributes F1, F2, F3, F4 and F5 and this is the candidate key. Candidate key is a F1, F2. F1, F2. Is it clear? What is that problem? A table has fields F1, F2, F3, F4 and F5 with the following functional dependency. Already given the functional dependency. What is the functional dependency? F1 tends to F3, F2 tends to F4, F1, F2 tends to F5. Functional dependency is nothing but x tends to y, y is depend on x, x is a determinant, y is the dependent. That is a y subset are equal to x. And what is the property of functional dependency? T1 of x equal to T2 of x, T1 of x equal to T2 of x, then T1 of y equal to T2 of y. That is a functional dependency property. Okay, whereas now I think you are familiar that based on the closure, we can easily find out the keys, candidate keys. What is the F1 closure? F1 closure is the F1, F1 derives F3. Okay, only we get F1, F3, but what is the actual original values? F1, F2, F3, F4 and F5. We can't get the original attributes, that's why F1 is not in candidate key. Next F2 closure, F2, F4. Okay, we can't get the original attributes. Okay, next F1, F2 closure. You write F1, F2. F1 derives what? That is the F3. F2 derives what? F4. F1, F2 derives F5. That's why you can get the original attributes. Here F1, F2 is a candidate key. F1, F2 is a candidate key. Observe here what is a tabular representation. Tabular representation. Here F1, F2, F3, F4, F5. F4, F5. And what is the combination here? F1, F2 is a key. F1, F2 is a key. What is the F1 tends to? F1 tends to F3. F2 tends to F4. F1, F2 tends to F1, F2 tends to F5. Observe here F1, F2 tends to F5. That is the non-key attribute is a F5. Is fully functional dependent on F1, F2. Whereas in the here, F2 and F1, that is a F2 is a part of primary key. And then F1 also is a part of primary key. That's why partially dependency is there. The given relation is not in second normal form. It is in first normal form. According to our options, that is the first answer is the correct. First normal form. Is it clear? That is what is the F1, F2, F1, F2, F1, F2, F1, F2 is a key. Candidate key. F1, F2 tends to F5. F1, F2 is a key. And whereas in the F1, given function F1, F2, F1 is a part of, and then F2 also is a part. That's why there is a partial dependency is there. In second normal form, there is no partial dependency. It is fully functionally dependent on primary key. Okay, that's why the given relation, the given problem is not in second normal form. It is in first normal form. Okay, first normal form states that it should be only simple or individual or atomic value. Okay, that is a, one example. Another example, that is a GATE 2008. A relation R of A, B, C, D, P, G, the following functional dependencies in terms of normalization. This table is in 1NF, 2NF, 3NF, none. Okay, observe here based on the functional dependency. Okay, first we find closure. Okay, observe here, and what is meant by C closure? Suppose C closure, we can derive CE. We can't get original values. CE only, remaining attributes are missed. That's why C is not a candidate key. And then P closure. What is a P closure? PC. That is a C derives what? E. Okay, that is a PC is there. P there, C is there, and then E is there. We miss remaining attributes. That's why that is a P is not a candidate key. And next B closure. B closure. What is a B closure? B derives what? That is a G. Observe here B and G. That is the remaining attributes are missed. We can't get the original table or original relation. That's why B is not a candidate key. And then next one DE closure. Right? DE based on the reflexive property. And then DE. And what the DE derives what? That is a P. And what the P derives what? C. And then C derives what? E. Okay, there is no combination. Next we miss, that is a B and A. That's why this is the D and E are not a candidate key. Right, whereas in the observe here last one AB closure. That is a AB. AB closure is a AB. Right, B derives what? That is a G. Right, AB derives what? CD. AB derives what? CD, and then B derives what? G, and then C derives what? E. DE derives what? P. Observe here, that is a, total 7 attributes is there. 1, 2, 3, 4, 5, 6, 7. That is A is there, B is there, C is there, D is there, E is there, P is there. Okay, that's why we can get the original relation. Here AB is a candidate key. AB is a candidate key. What is meant by candidate key? The minimal super key is called candidate key, or the set of all the keys in a relation is nothing but candidate key. That is a AB is a candidate key. Okay, keep in your mind before going to the problem. First we find the closure. If you familiar closure and keys concept, we can easily solve this type of problems. Right, what is the first one? AB. Observe here AB. AB is a primary key or AB is a candidate key. AB is a candidate key. That is a AB tends to what? That is a CD. AB tends to CD. Observe here B tends to G. B tends to G. B tends to G is a part of a primary key. But here non-key attributes is fully functional dependent on primary key. Here B tends to G. B tends to G is a part of primary key. That's why partially dependence is there. Partial dependency. Partial dependency is there. Okay, that is a drawback in second normal form. That's why the given relation is not in second normal form. Is not in second normal form. It is in first normal form. The given option is the first option. Okay, what is my second normal form? A relation schema R is in the second normal form. For every non-key attribute is fully functionally dependent on primary key. Here, based on the problem, what is the R of A, B, C, D, E, P, G? The following functional dependency in terms of normalization, this table is in first normal form or second normal form or third normal form or BCNF. Okay, before going to this problem, what is my functional dependency? What is my super key? What is my primary key? What is my candidate key? Okay, I think you are familiar that these terminology we can easily solve this type of problem. Okay, what is the first one? We find that is a closure. Why you can choose closure? We can find key values. Okay, that is a candidate keys. Okay, that's why C closure, CE, we miss the attributes. P closure, we cannot get the original relation. B closure, we cannot get the original relation. DE closure, we cannot get the original relation. AB closure, we can get the original relation. AB is a candidate key. Okay, according to our definition, second normal form, what is the partial dependency? There is no partial dependency in second normal form. But observe here, AB tends to CD. AB is a primary key. Here B tends to G is a part of primary key. Okay, that's why is not in the second normal form, it is in first normal form. Okay, that is the, today topic, second normal form. In next class, we are going to discuss third normal form. What is my third normal form? Okay, what is the importance of third normal form? Okay, what is the difference between third normal form and Bayes code normal form? That we will see in the next class. Thank you.